What if the universe, in its unfathomable grandeur, holds its breath, waiting for you to look before it decides what to be? This isn't a question from the pages of philosophy or a forgotten mystic text. It is the haunting empirical conclusion that whispers from the very heart of physics, born from an experiment so simple in its design, yet so profound in its implications, that it has shattered our perception of everything we thought was real. For over a century, it has stood as a formidable challenge to our collective intellect, a cosmic riddle posed in a language of light and shadow. It suggests that the bedrock of reality, the very fabric of existence, might be a shimmering, undecided phantom until the moment it is observed. This is the story of a journey into the quantum realm, a place where logic bends and intuition fails, all illuminated by two simple slits in a barrier. It is the story of the Double-Slit Experiment, and it begins not with a cataclysmic explosion or a distant galaxy, but with the quiet journey of a single particle of light, a journey that will force us to question whether the world we see is a world we ourselves help create. To grasp the enormity of the paradox, we must first build the world that makes sense, the world of our everyday experience. Imagine a wall perfectly opaque, and in it, we cut two thin, parallel vertical slits. On one side, we place a device that can fire tiny pellets, like microscopic marbles, one after another. On the other side of the wall, we place a detector screen, a backstop that will record exactly where each pellet lands. Now, we begin. We close one slit and fire our stream of marbles. The result is perfectly predictable, a tight cluster of impacts on the screen directly behind the open slit. It's what our intuition, honed by a lifetime of interacting with a tangible world, expects. The marbles that pass through the opening continue in a relatively straight line and strike the screen. If we close that slit and open the other, we get an identical result, just shifted in position. A second tight cluster forms directly behind the newly opened slit. Again, this is simple, mechanical, and reassuring. It's a universe of cause and effect, of solid objects following predictable paths. So, what happens when we open both slits at once? The answer seems insultingly obvious. We will get two distinct bands on the screen, a perfect combination of the first two experiments. Each marble, being an indivisible solid object, must pass through either the left slit or the right slit. There is no other option. Those that go through the left contribute to the left band. Those that go through the right contribute to the right band. The final pattern is a simple sum of the two possibilities, a clear and unambiguous record of tiny objects taking one of two definite paths. This is the classical world, a realm of certainty and solidity. It is the world Isaac Newton described, a grand, clockwork mechanism where everything has a place and a trajectory. For centuries, we believed this was the only world there was. We were wrong. Now let us change the experiment. We will keep the barrier with its two slits and the detector screen, but instead of firing marbles, we will shine a light. For a very long time, light was thought to be composed of tiny particles, or corpuscles, as Newton called them. If that were true, we should get the exact same result as we did with the marbles, two distinct bands of light on the screen. But in the early 1800s, a brilliant physician and polymath named Thomas Young dared to challenge this view. He proposed that light was not a particle but a wave, an undulation propagating through a mysterious ether, much like ripples spreading across the surface of a pond. His proof was this very experiment. When he shone a single coherent beam of light through both slits simultaneously, the pattern that emerged on the screen was not two simple bands. Instead, what appeared was a breathtaking tapestry of alternating bright and dark stripes, a pattern of interference. It was a mathematical hymn written in photons. The brightest band was in the very centre, a place where, logically, the solid barrier should have cast a shadow. Flanking it were stripes of pure darkness, and then more stripes of light, fading in intensity as they moved outward. This is the quintessential signature of waves. Imagine again the ripples in a pond. When a wave passes through the two slits, it's like two new synchronized waves are created, one from each opening. As these two new waves spread out and overlap, they interfere with each other. Where the crest of one wave meets the crest of another, They amplify, creating a larger wave. This corresponds to a bright band of light. But where the crest of one wave meets the trough of another, they cancel each other out completely, resulting in nothing, a dark band. The very existence of this interference pattern was irrefutable proof. Light was a wave. It could be in two places at once, passing through both slits simultaneously, interfering with its own ghostly twin to produce the intricate pattern on the screen. The debate seemed settled, but the 20th century, with the birth of quantum mechanics, would resurrect the debate with a vengeance, adding a layer of mystery that borders on the supernatural. Scientists developed the incredible ability to control light with unprecedented precision. They could now conduct Young's experiment not with a continuous wave, but with a single indivisible packet of light, a photon, one at a time. Here, the paradox truly takes root and begins to strangle our understanding of reality. Think about what this means. We can fire a single photon from our source. It is an elementary particle, the fundamental unit of light. It cannot be split in half. Like one of our tiny marbles, it must make a choice. It must go through the left slit or the right slit. It cannot, by any logical definition, go through both. If we fire millions of these photons, one after another, with minutes or even hours between each launch, we should, by all accounts, slowly build up the simple, two-band pattern we saw with the marbles. Each photon makes its independent journey, strikes the screen, and creates a single dot. Over time, these dots should form two distinct lines, a record of which slit each individual particle chose. And so, the experiment is run. The laboratory is hushed. The instruments are calibrated. The first photon is released. It streaks across the empty space, a solitary traveller on an unknown path. It strikes the screen, leaving a single tiny point of light. A second photon is launched, then a third, a fourth. For hours, the process continues, a patient accumulation of single, isolated events. At first, the pattern of dots on the screen seems completely random, a meaningless scattershot. There is no order, no hint of what is to come. But as we continue, as thousands, and then millions, of individual photon impacts are recorded, a ghostly image begins to coalesce from the chaos. It is not the two bands of the particle world. Impossibly, miraculously, it is the interference pattern. The alternating bands of light and dark emerge, built dot by single dot. Pause here and consider the terrifying abyss of logic this result opens before us. Each photon was fired alone. There were no other photons for it to interfere with. And yet the final pattern is one of interference. It's as if each individual photon, on its solitary journey, somehow passed through both slits at once. It behaved like a wave, interfering with itself, a self that took a path that the particle version of itself did not. How could it possibly know about the other slit? How could a single particle, arriving at the screen as an indivisible point, have carried with it the information about two separate paths? It's as if it travelled not as a thing, but as a cloud of pure potential, a phantom wave of probability that explored every possible route simultaneously. This wave of possibility passed through both slits, interfered with itself, and then, upon striking the screen, the wave collapsed and the photon materialized in a single spot, its location dictated by the ghost wave that guided it. The implications are staggering. The universe, at its most fundamental level, seems to be a realm of undecided possibilities, of spectral potentialities. An object can be both a particle and a wave, a bullet and a ghost, its nature fluid and undefined. This paradox was so profound, so deeply unsettling, that the greatest minds in physics, including Albert Einstein himself, refused to accept it. It felt like a trick. It felt like the universe was playing games with us. So they devised a way to outsmart it. They decided to watch. The core of the mystery, they reasoned, was the photon's journey. Which slit did it really go through? To find out, they placed a sophisticated detector, a microscopic gatekeeper, at the slits themselves. This detector would be so sensitive that it could register the passage of a single photon, telling us, once and for all, whether it went through the left slit or the right. It would not block or destroy the photon, merely record its path. It was a simple question posed to nature. Show us the way. With this detector in place, the experiment was run again, one photon at a time. The physicists watched their monitors, ready to finally solve the enigma. And what they saw destroyed our last vestiges of a classical objective reality. The moment they turned on the detector to see which path the photon took, the interference pattern vanished completely, instantly. The alternating bands of light and dark dissolved, replaced by the two simple, mundane bands we saw with the marbles. The very act of observing the photon's path, the act of knowing which slit it went through, forced it to behave like a simple particle. By looking, we had compelled the universe to make a choice. The moment we measured its position, the ghostly wave of potential outcomes collapsed into a single, concrete reality. The photon, now under our gaze, picked a slit and flew straight through it. Its wave-like nature, its ability to be in two places at once, simply ceasing to exist. If we turn the detector off, the interference pattern immediately returns. The photon once again becomes a wave of possibility, passing through both slits simultaneously. Look, and it's a particle. Don't look, and it's a wave. Let the weight of this sink in. The behavior of a fundamental particle of reality changes based on whether or not we are watching it. This isn't a matter of the detector somehow physically disturbing the photon. The experiment has been refined over decades to the point where the interaction is impossibly gentle. It is the acquisition of information itself, the knowledge of which path, that seems to be the critical ingredient. The universe behaved differently because it was being measured. This strikes at the very foundation of science, the assumption of an objective reality that exists independent of the observer. The double-slit experiment suggests that this assumption may be fundamentally wrong. It presents us with a cosmos that is not a static, pre-existing stage on which events unfold, but a dynamic participatory system where the observer is not a passive spectator, but an active creator of reality. We are left with questions that resonate far beyond the walls of a physics laboratory, questions that touch upon the nature of consciousness, information, and existence itself. What is the true nature of an electron or a photon before it is measured? Does it even have a definitive state? Or does it exist in a ghostly superposition of all possible states, a seething ocean of potential? What constitutes an observation? Does it require a conscious human mind, or is any interaction with another particle, any recording device, enough to collapse the wave of possibility? Are we, through our senses and our instruments, constantly pulling a definite reality out of an indefinite quantum fog? This single experiment, elegant in its simplicity, has become the cornerstone of quantum mechanics, and in doing so, has become the greatest mystery in all of science. It is a gateway to a universe far stranger and more interconnected than we could ever have imagined, a universe where the line between the observer and the observed blurs into non-existence. As we venture deeper into this enigma, we will find that these questions do not have easy answers. Instead, they lead us further down the rabbit hole to a place where reality itself seems to be little more than a dance between possibility and perception. What is the fundamental substance of our world? If you could peel back the layers of reality, past the cities and forests, beyond the molecules and atoms, what would you find at the very bottom? Is it something solid, something definite, like an infinite collection of microscopic marbles clicking against one another through the ages? Or is it something more ethereal, a universe of shimmering vibrations, a cosmic ocean of overlapping waves carrying energy and information? For most of human history, this was a question for philosophers, a debate for late nights and flickering candles. But at the dawn of the 20th century, it became the single most urgent, most confounding question in all of science. A question that would force us to abandon the solid ground of common sense and venture into a reality more strange than any mystic could have ever conceived. Our journey begins in a world that felt to its inhabitants perfectly understood. The great clockwork universe, wound up by a divine hand and set in motion by immutable laws, was the masterpiece of Sir Isaac Newton. His mechanics described the majestic dance of the planets and the simple fall of an apple with the same breathtaking precision. everything had its place, a definite location, and a predictable trajectory. It was a universe of certainty, a cosmos of solid, dependable things. And this philosophy of the concrete, of the tangible, extended even to the most mysterious phenomenon of all, light. For Newton, light was not a wave, not a vibration in some unseen medium. It was a stream of impossibly tiny, fast-moving particles which he called corpuscles. These corpuscles, he argued, shot out from a candle flame or the sun in perfectly straight lines, like infinitesimally small bullets. When they struck your eye, you experienced sight. When they bounced off a mirror, they ricocheted just as a ball would. When they passed through a prism, the different sizes of corpuscles were sorted by the glass, creating the colours of the rainbow. It was a beautifully simple, mechanical, and intuitive picture. It fit perfectly within his clockwork cosmos. For over a century, Newton's authority was so absolute that his particle theory of a light was less a theory and more an article of faith. There were, of course, dissenting voices. The Dutch scientist Christian Huygens, a contemporary of Newton's, had proposed a radically different idea. He suggested that light was not a particle at all, but a wave spreading through a mysterious invisible substance he called the luminiferous ether, much like ripples spread across the surface of a pond. Huygens's wave theory could explain reflection and refraction just as elegantly as Newton's. Imagine a wavefront hitting a shoreline at an angle. It bends, it changes direction. But his idea posed difficult questions. What exactly was this ether? And more problematically, waves are known to bend around obstacles, a phenomenon called diffraction. If light were a wave, shouldn't we see it bend around corners? Shouldn't a sharp shadow have fuzzy, indistinct edges? The shadows we see every day seemed razor-sharp, a powerful argument for Newton's straight-flying particles. For 100 years, the sheer weight of Newton's legacy crushed Huygens's delicate wave theory. The universe, it was decided, was made of things, and light was one of them. The case appeared to be closed. But science is a restless enterprise. It has a habit of revisiting closed cases, of picking at threads that seem neatly tied. The thread that would unravel Newton's theory of light came from the mind of one of history's greatest polymaths. His name was Thomas Young, and in the year 1801 he devised an experiment so simple in its design, yet so profound in its implications, that it remains the single most important experiment in all of quantum physics, the bedrock on which our entire modern understanding of reality is built. Young was a physician, a physicist, a linguist, who helped decipher the Rosetta Stone. He was a mind unbound by convention, and perhaps that is why he could see what others had missed. He decided to put the nature of light on trial, to force it once and for all to reveal its true identity. The apparatus he constructed was ingeniously simple. He took an opaque barrier, something as simple as a piece of card, and cut a single thin vertical slit into it. He then placed this barrier in a beam of sunlight. On a screen behind the barrier, as you would expect, a single bright line of light appeared, a faithful projection of the slit. It was a result that told you very little. Both a wave and a stream of particles passing through a single opening would produce a nearly identical pattern. The genius of the experiment, the twist that would change the world, was what Young did next. He took another barrier, this one with two impossibly thin parallel slits, placed very close together, and he put it between his first barrier and the viewing screen. He was now forcing the single beam of light to split, to pass through both openings simultaneously, before continuing its journey to the screen. Here, in this simple arrangement, lies the heart of the matter. Here, we can finally ask our question directly. Light, what are you? A particle or a wave? The beauty of this experiment is that these two possibilities predict wildly different outcomes. It is not a matter of subtle shades of grey, it is a clear choice between two mutually exclusive realities. Let's imagine for a moment, as Newton did, that light is a stream of tiny particles, like microscopic grains of sand shot from a spray gun. What would we expect to see on the screen behind the two slits? Common sense gives us a clear and unambiguous answer. Some particles would travel through the left slit, others would travel through the right slit. They would continue in their straight lines and strike the screen behind. Over time, you would build up a pattern. Directly behind the left slit, a bright band would form, a pile-up of all the particles that took that path. Directly behind the right slit, an identical bright band would form, the destination for all the particles that went through the other opening. The final pattern would be simple: two distinct bright lines, separated by a dark space in the middle. It is the only logical outcome. Each particle must pass through one slit or the other. It cannot be in two places at once. The total pattern on the screen must simply be the sum of the particles arriving from the left slit and the particles arriving from the right slit. This is the world as we know it, the classical intuitive world of solid objects and definite paths. This is the result Newton would have wagered his reputation on. This is the particle prediction. But what if Huygens was right? What if light is not a particle, but a wave, propagating through space like a ripple on a cosmic pond? What would we expect to see then? To understand this, we must first think about how waves behave, not in the abstract realm of light, but in a familiar setting, like a calm pool of water. If you create a wave that passes through a single slit in a barrier, it spreads out on the other side in a semicircular pattern, a new circular ripple emanating from the opening. This is diffraction, the very phenomenon that had once been used as an argument against the wave theory. But what happens when you have two slits? As the initial wavefront strikes the barrier, it passes through both slits at the same time. Each slit now acts as a source for its own new circular wave. You now have two separate sets of ripples spreading out from the two openings, and this is where something magical happens. These two sets of waves begin to interfere with each other. Where the crest of one wave meets the crest of another, they combine their energy. They lift the water higher. This is called constructive interference. The result is an amplified wave, a point of maximum intensity. But where the crest of one wave meets the trough of another, they cancel each other out. The upward push of the crest is perfectly nullified by the downward pull of the trough. The water at that point becomes perfectly still, perfectly calm. This is destructive interference, a point of zero intensity. So what pattern would these overlapping water waves create on a screen or a shoreline placed behind them? You wouldn't see two simple splashes corresponding to the two slits. Instead, you would see a far more complex and beautiful pattern. There would be a point of intense activity directly in the middle, a place where waves from both slits have travelled the exact same distance and arrived crest to crest. Flanking this central point, there would be regions of complete calm, where the waves have cancelled each other out, and beyond those, another set of intense splashes, and then more calm, and so on. The result would be a series of alternating bands of high and low intensity, a striped pattern known as an interference pattern. It is the unambiguous signature of a wave. It is something that particles, in their straightforward individual journeys, could never, ever produce. So the stage was set, the question was posed. The two possible answers were clearly defined on the wall. Would light behave like a stream of sand, creating two simple bands, or would it behave like a water wave, creating a complex pattern of many alternating stripes? Thomas Young darkened his room, allowed a thin pencil of sunlight to enter, and let it fall upon his two slits. He held his breath, and he looked at the screen. What he saw in that moment was not a guess, not a philosophy, but a message delivered directly from nature itself, and the message was breathtaking. There on the screen, shimmering in the dusty air, was not the simple two-band pattern predicted by Newton. Instead, a series of exquisite, ghostly, alternating bright and dark fringes stretched across the screen. A central bright band flanked by darkness, then another pair of bright bands, then more darkness, fading out towards the edges. It was, without a shadow of a doubt, an interference pattern. The verdict was in, the centuries-long debate was over. Huygens had been right all along. Light was a wave. It was an earth-shattering conclusion. It demonstrated that something could pass through two separate openings at the same time, interfere with itself, and create a pattern that could only be explained if it had taken both paths simultaneously. How could this be? A particle is a thing a discrete object located at a single point in space. It must choose a path. A wave, however, is a distributed disturbance, an excitation spread out in space. It doesn't have a single location. When the wavefront meets the two slits, it doesn't have to choose. Part of it goes through the left, and part of it goes through the right. It is the subsequent recombination of these two parts of the same wave that creates the ethereal stripes on the screen. The bright bands were the regions of constructive interference, where the two paths of light arrived in perfect sync, their energies combining. The dark bands, the mysterious voids of nothingness, were the regions of destructive interference, places where light plus light somehow miraculously equal darkness. It was a perfect, unambiguous and stunning victory for the wave theory. Young's experiment was a masterpiece, a cosmic interrogation that had forced the universe to confess one of its deepest secrets. The implications rippled outwards, transforming our understanding of the world. For the next 100 years, physics was built upon this new certainty. The particle theory of light was relegated to the dustbin of history, a charming but mistaken idea from a previous age. The triumph of the wave theory was cemented in the 1860s by the brilliant Scottish physicist James Clerk Maxwell. He was working on the seemingly unrelated phenomena of electricity and magnetism. Through a set of 4 breathtakingly elegant equations, he unified them, showing they were two sides of the same fundamental force, electromagnetism. But his equations held a surprise, a stunning prediction. They showed that a changing electric field creates a changing magnetic field, which in turn creates a changing electric field, and so on. This self-propagating disturbance would travel outward as a wave, moving at a very specific speed. When Maxwell calculated this speed from his laboratory measurements of electric and magnetic forces, he arrived at a number that was shockingly familiar, 186,000 miles per second. The speed of light. The conclusion was inescapable. Light was an electromagnetic wave. Its colours were simply different wavelengths of this radiation. Its energy was carried in the undulating dance of electric and magnetic fields. It was the final, triumphant confirmation of Thomas Young's discovery. The universe, it seemed, was finally making sense. Its foundations were waves and fields, governed by elegant mathematical laws. The cosmos was no longer a collection of tiny clicking marbles, but a grand, vibrating symphony. A sense of profound order and understanding settled over the world of physics. The great mysteries had been solved. We had looked at the very essence of light, and it had given us a clear, consistent and beautiful answer. For a glorious moment it seemed as if we finally understood the fundamental nature of our reality. The case was closed. The book was written. Or so it appeared. This beautiful, satisfying picture of a wave-like world was the pinnacle of classical physics. It was a foundation so solid, so well confirmed by experiment, that to question it would have been madness. Yet, even as this grand cathedral of knowledge was being completed, strange new discoveries were being made in the basements of laboratories. Physicists were developing tools that could probe the world with unprecedented delicacy, tools that could investigate not just a massive beam of light, but its interaction with individual atoms. They were about to rerun Thomas Young's experiment, not with the blinding glare of the sun, but with a light so faint, so impossibly dim, that they could ask it a new and far more personal question. A question that would shatter the classical world forever and reveal a paradox at the very heart of existence. They were about to ask what light is doing, not as a collective wave, but one particle at a time. And so, with the rules of the game seemingly established, we left the sun-drenched world of classical physics, a world of comforting certainty, where waves were waves and particles were particles. It was a realm governed by tangible laws, as reliable as the tides, where a thrown stone followed a predictable arc and a ripple in a pond spread with mathematical grace. The universe, it seemed, was a grand and intricate clockwork mechanism, and we, its clever inhabitants, were finally beginning to understand how to read its face. But the deepest truths are rarely found in the light. They wait for us in the shadows, in the spaces between what we think we know. The next step in our journey required a descent, a move away from the vast and the visible, into a domain so small, so alien, that the familiar rules of our world would not just bend, but shatter into 1,000 impossible pieces. The call to adventure for physicists of the early 20th century was not a journey to a new continent, but a voyage into the heart of the atom. They needed a new kind of vehicle, a new tool to probe this bewildering landscape. Their idea was deceptively simple, a refinement of the experiment that had already given them such clean, elegant answers. They would take the double-slit experiment, this perfect divider of worlds, and push it to its absolute limit. Instead of a torrent of light or a cascade of sand, they would attempt something of breathtaking technical audacity. They would fire just one particle at a time, not a stream, not a volley, a single, solitary traveller on a journey toward the twin gateways. The particle of choice was the electron, that quintessential building block of matter, the tiny, indivisible bullet we imagined orbiting the nucleus of every atom. Imagine the scene. A laboratory, shielded from the vibrations of the outside world, humming with the low thrum of vacuum pumps and high-voltage equipment. Here, scientists had constructed what was essentially a microscopic machine gun, an electron emitter capable of firing its ammunition one by one by one. Each electron would be launched in isolation, traversing the empty space of the vacuum chamber alone. It would speed toward the barrier with its two slits, and on the far side, a detector screen, a piece of sophisticated photographic film, would wait patiently to record its arrival. A single, tiny point of light would mark the final destination of each microscopic voyager. This wasn't about waves anymore. This was about ballistics. It was about tracking a single entity, a lone citizen of the material world, and proving, once and for all, that the universe, when you boiled it all down, was made of solid, predictable things. The prediction was trivial, a foregone conclusion based on centuries of watching the world work. It was the common sense of Newton and Galileo writ small. If you fire a single bullet at a wall with two openings, it can only go through one. It cannot split itself in two. It cannot pass through both simultaneously. Therefore, over time, as you fire thousands of these individual electrons one after another, with long pauses in between to ensure they never interact, you should see a pattern form on the screen behind. What would that pattern be? Two simple, distinct bands of impacts, each one a perfect shadow of the slit through which its respective electrons passed. A pile of hits behind the left slit, and a pile of hits behind the right slit. Anything else was physically, logically, philosophically impossible. This experiment wasn't expected to uncover a mystery. It was designed to eliminate one, to confirm the particle nature of the electron with brute, mechanical force, and close the book on any lingering classical confusions. It was meant to be the final triumphant validation of our material reality. The machine is switched on. A single electron is released. It is a lonely pilgrimage, a journey of a few millionths of a second across a silent void. It strikes the detector screen. Click. A single point appears, a moment of quiet. Then another electron is fired. It too makes its solitary voyage. Click. Another dot appears on the screen in a different location. The process is repeated again and again. An hour passes. Thousands of electrons have been fired, each one an independent event, completely unaware of the sibling particle that came before it or the one that will come after. They are like solitary raindrops falling on a pavement, each one leaving its own separate mark, a record of its lonely impact. The physicists watch the data accumulate, expecting to see the two familiar mundane bands slowly take shape, the ghost of the two slits materializing from the scattered points of light. But as the minutes turn into hours, and the number of impacts grows from thousands to tens of thousands, a horrifying, beautiful, and utterly impossible picture begins to emerge from the static. It is a pattern that should not exist. It is a message from an alien reality. Slowly, inexorably, the dots on the screen are not clumping into two simple bands. Instead, they are arranging themselves into a series of multiple, alternating stripes of light and dark. A bright band of many impacts. Next to it, a dark band with almost no impacts. then another bright band, then another dark one. It is the unmistakable signature pattern of interference. It is the pattern of waves, the very pattern that a single, indivisible particle was never, ever supposed to create. Let the sheer bone-deep strangeness of this sink in. This is the moment the clockwork universe broke. This is the discovery that haunts the dreams of physicists to this day. The interference pattern, the hallmark of waves cancelling and reinforcing each other, was appearing on the screen. But for waves to interfere, you need at least two of them. A wave passing through the left slit must interact with a wave passing through the right slit. That is the only way to produce these alternating bands of constructive and destructive interference. Yet, there were no waves. There was only ever one electron in the entire apparatus at any given time. Each electron was fired long after the previous one had completed its journey and made its mark. There was nothing for it to interfere with. The conclusion is inescapable, a logical abyss from which there is no retreat. For that single electron to create a pattern that depends on the existence of both slits, it must have, somehow, gone through both slits at the same time. The single, indivisible particle had to have been in two places at once. It had to have interfered with itself. This is not a metaphor. It is not a clever analogy. It is the brutal, paradoxical truth that the experiment revealed. The electron leaves the emitter as a single, particle-like entity. It arrives at the detector screen as a single, particle-like entity, creating one tiny dot. But in the unobserved, unseen journey in between, it behaves as if it were a wave, a ghostly ripple of pure potential that explores every possible path simultaneously. It is a wave that passes through the left slit and a wave that passes through the right slit, both at the same time. These two phantom versions of the same electron then move forward, interacting with one another, creating the characteristic ripples of interference, before finally collapsing back into a single particle at a single point the moment they hit the screen. The electron, it seems, is a creature of profound duality. It is a particle when you look for it, but a wave of possibility when you do not. This is not a flaw in our equipment. It is not a misinterpretation of the data. This is the fundamental nature of reality itself. Every single particle in the universe, every electron, every proton, every photon of light, possesses this ghostly, schizophrenic identity. When we are not observing them, they do not exist in one definite place. Instead, they exist in a state of superposition, a smear of probabilities, a cloud of potential. An unobserved electron isn't a tiny marble hurtling through space. It is a wave of what could be, a mathematical description of its own likelihood of being found here or there or anywhere else it is allowed to go. It is in all possible states at once. The very act of its journey through the two slits is not a choice between left or right. It is an embrace of both. It is a phantom entity, a whisper of existence that takes every road at once. This concept, superposition, is the bedrock of quantum mechanics, and it is a direct assault on our most deeply held intuitions about the world. We are built to experience a universe of singular, definite realities. A chair is either in the room or it is not. A door is either open or it is closed. You are here, now, reading this. You're not simultaneously here and on the far side of the moon. This is the reality we call classical, the one we can touch and see. But the Double-Slit Experiment tears back the curtain on this comfortable stage play, revealing the bizarre machinery operating behind the scenes. It tells us that at the most fundamental level, the universe is not made of things, but of possibilities. An electron, before it is measured, is not a thing at a place, but the potential for a thing to be at all places. Its reality is probabilistic, not deterministic. It walks a quantum tightrope between being and non-being, between here and there, a state of pure information that only resolves into a concrete fact, a dot on a screen, when it is forced to interact with the larger world. Think of what this means. The electron knows that both slits are open. The presence of the second slit, a path it could have taken but, in our classical minds, did not, fundamentally alters its behaviour. If you close one of the slits, the interference pattern vanishes instantly. With only one path available, the electrons behave as they should, piling up in a single boring band behind the open slit. But open the second slit again, and the ghostly interference bands reappear. The mere possibility of an alternate route changes the outcome. The universe, it seems, is not just a collection of facts about what is. It is also shaped by the ghosts of what might have been. The roads not taken leave their fingerprints on reality. This discovery was a cataclysm for physics. It was as if astronomers, after centuries of mapping the stars, looked through a new telescope and discovered the sky was a projection on a dome, with something utterly unknown operating behind it. The clockwork certainty of Newton was replaced by the cosmic casino of quantum mechanics. The world was no longer a machine. It was a shimmering fabric of possibility. It introduced a fundamental fuzziness, a layer of irreducible uncertainty into the heart of creation. We could no longer predict with certainty where a single electron would land. We could only predict the probability. We could point to the bright bands of the interference pattern and say, it will probably land here. But we could never, ever know for sure. The universe, at its core, gambles. This revelation split the world of physics in two. For some, like the Danish physicist Niels Bohr, it was a profound truth to be accepted. The old notions of reality were simply a convenient illusion, a large-scale approximation that breaks down in the quantum realm. The particle simply does not have a definite position until it is measured. To even ask where it was before it was observed is a meaningless question, like asking for the political views of a rock. For others, like Albert Einstein, this was an absurdity, a sign that the theory was incomplete. God does not play dice, he famously protested. There had to be a deeper, hidden reality, some unknown variable that was guiding the electron on its path, creating the illusion of randomness. He could not accept a universe whose foundations were built on probability and ghosts. But decades of subsequent experiments have only deepened the mystery and confirmed the bizarre conclusion. The ghostly wave of superposition is real. A single particle can and does exist in multiple states at once, taking multiple paths through space-time. We are left staring at the screen, at that impossible pattern of light and dark bands, a message written in the language of probability by single, solitary electrons. Each dot is a testament to a journey that defies logic, a journey through a forking labyrinth where every path was taken. We had set out to prove the simple, solid, particle nature of our world. Instead, we found that reality is a phantom, a wave of potential that only solidifies into fact under the harsh glare of observation. And this very conclusion, opens up an even more disturbing and profound question, a question that would lead physicists down an even deeper rabbit hole. If the electron behaves like a wave when we are not watching it, and a particle only when it hits the screen and is observed, then what counts as an observation? What is this magical process that forces the universe to choose to collapse the ghostly wave of infinite possibilities into one single, concrete reality? The experiment had shown us what matter does when left to its own devices, in the dark. The next, terrifyingly logical step was to try and catch it in the act, to peek behind the curtain. To place a detector at the slits themselves and ask the electron a simple, direct question. Which path did you really take? The answer to that question would prove to be more shocking, more reality-bending than the interference pattern itself. It would suggest that the universe is not just strange. It would suggest that the universe knows when it is being watched. The ghost was in the machine. A single electron, which should have been a point of absolute certainty, was behaving like an apparition, a phantom spreading itself across possibilities to perform an impossible feat of self-interference. It left behind not the evidence of a journey, but the ghostly imprint of a wave, a ripple in the fabric of what we thought was solid reality. For science, for a discipline built upon the bedrock of causality and tangible evidence, this was not just a puzzle, it was an affront. An elegant, maddening and beautiful defiance of common sense that could not be allowed to stand without a challenge. Humanity's collective intellect, faced with this quantum spectre, did what it has always done when confronted by the inexplicable. It decided to turn on the lights. It decided to look. The logic was as simple as it was profound. If a single particle is somehow travelling through both slits at once to create this wave pattern, then the most direct way to solve the riddle is to watch it. We needed a witness. We needed to post a guard at the gates and force the electron to declare its allegiance. The question we would pose to the universe was brutally direct. Which path did you take? To ask it, physicists devised an instrument of exquisite sensitivity, a form of microscopic gatekeeper. Imagine a detector, a hyper-advanced sensor placed right at one of the slits, or both. This device would be a silent, impassive observer, engineered to do one thing and one thing only: register the passage of an electron. It wouldn't stop it or harm it. It would merely note its presence with a subtle click, a blip of data, a whisper of information that said, "It came this way." This was not a passive act. This was an interrogation. We were setting a trap for a fundamental particle, attempting to force its nebulous, ghostly nature into a concrete, definitive answer. The experimental chamber was no longer just a sterile environment for observation, it became an arena. In one corner, the electron, a quantum entity cloaked in the mathematics of probability waves. In the other, the full force of human curiosity, armed with a detector designed to pierce that veil of uncertainty. The goal was to catch the magician in the act, to see precisely how the trick was being done. Physicists around the world held a collective breath, anticipating the moment of clarity. Surely by knowing the path, we would finally understand the mechanism. The wave-like behaviour would be revealed as some subtle, yet undiscovered classical process, and the world would make sense again. The universe, we presumed, was not shy. It would give up its secrets under direct questioning, so the experiment was reset. The electron gun was primed to fire its solitary projectiles one by one. The double slits were waiting, two silent invitations into the unknown. But now, they were guarded. The detectors were switched on, humming with a quiet energy, their electronic sensors poised to catch the faintest whisper of a passing particle. The first electron is fired. It hurtles across the vacuum, it approaches the barrier, and then a signal, a definitive, unambiguous ping from the detector at the right slit. The screen at the back registers a single point of light. A success. The guard has done its job. We know with absolute certainty that the electron behaved like a respectable particle and passed through the right-hand slit. Another electron is launched. This time, a ping from the left detector. Another single dot appears on the screen. And so it continues. Ping, left, ping, right, ping, right. A stream of data flows in, crisp and clear. For a moment, there is a feeling of profound relief, the intellectual satisfaction of a problem solved. The phantom has been exorcised. The electron, when observed, is not a wave at all. It is a particle, a tiny bullet. Just as our intuition has always told us, it chooses one path and one path only. The mystery, it seems, was nothing more than an artifact of our own ignorance, a ghost that vanished the moment we had the courage to stare it in the face. We let the experiment run, allowing thousands, then tens of thousands, of these individual, well-behaved electrons to accumulate on the screen. Each one dutifully reports its position, its path logged and recorded. Each one contributes its tiny point of impact to the final portrait we are painting of reality. But as that portrait takes shape, the feeling of relief begins to curdle. It slowly sours into confusion, then into a deep and chilling disbelief. Because the pattern emerging on the screen is not the one we remember. The familiar zebra-like stripes of the interference pattern, those alternating bands of certainty and nothingness, are gone. They have vanished completely. In their place are just two distinct solid bars of light, clustering directly behind each slit. It is the exact pattern we would expect if we were firing microscopic marbles through two holes, a simple, boring, classical result. There is no interference. There are no forbidden zones, no waves cancelling each other out. There is only the straightforward accumulation of particles that have picked a path and stuck to it. The ghost is gone, yes. But it seems to have taken the magic with it. The very act of watching, the simple, seemingly innocent act of asking, "Which way did you go?" has not just revealed the electron's true nature, it has fundamentally, impossibly altered it. Let the weight of this settle in. We did not touch the electron. We did not bombard it with some clumsy disruptive force. The detectors were designed for minimal interaction, a touch as light as a feather. All we did was gain knowledge. We acquired a single bit of information, left slit or right slit, and the instant we knew, the instant that information was registered in our apparatus, the electron behaved differently. It abandoned its ghostly, wave-like exploration of all possible paths. It renounced its quantum nature. It snapped into a single, mundane reality and flew straight, like a well-aimed stone. It's as if the universe itself possesses a kind of cosmic stage fright. As long as no one is watching, it performs a beautiful, impossible dance of wave-like probability. But the moment an observer looks, the moment a detector is switched on, the dance stops. The curtain falls. The performer freezes, pretending it was just standing there all along. Scientists, baffled and enthralled, ran the experiment again and again, trying to find a flaw, a loophole. They turned the detectors on. The interference pattern vanished, replaced by two simple clumps. They turned the detectors off. The interference pattern returned in all its mysterious glory. On, particle behavior. Off, wave behavior. The transition was instantaneous. It was absolute. It was as if a law of nature as fundamental as gravity was being written before their very eyes. The law of observation. The universe, it appeared, was playing a game of quantum peekaboo. When we cover our eyes, it is a wave of infinite possibilities. When we look, it is a particle in a single boring place. This phenomenon was given a name that is both deceptively simple and bottomlessly complex: the collapse of the wave function. The wave function is the mathematical description of that ghostly cloud of possibilities the electron inhabits when unobserved. It contains the potential for it to be here, or there, or in many places at once. The act of measurement, of observation, does something violent to this cloud. It forces it to collapse, to pop like a soap bubble, leaving only one single actualized reality in its place. The detector at the slit doesn't just see the electron. It forces the electron to exist, right there, as a particle. Before that moment of measurement, the electron was, in a very real sense, pure potential. It was a mathematical abstraction, a wave of probability washing over the entire experimental setup. The measurement is the act of creation. It is the cosmic anchor that drags the ghostly ship of quantum possibility into the safe harbour of a single defined reality. We, the observers, are not passive witnesses to the universe. We are participants. Our questions, our measurements, the very act of our knowing, seems to reach back and dictate the nature of what we're observing. Reality, at its most fundamental level, does not seem to be a fixed, objective thing that exists independent of us. Instead, it appears to be a fluid, indeterminate state that only congeals into a concrete form when it is measured, when it is forced to answer our questions. This raises a cascade of dizzying philosophical questions that science had never before been equipped to ask. What precisely constitutes an observation? Does it require a conscious human being? Did the wave function wait billions of years to collapse until the first physicist built a detector? Or is any interaction, however small, an observation? If a single photon bounces off the electron and carries away information about its path, even if that photon is never detected by us, is that enough to collapse the wave? Is the universe constantly observing itself, collapsing its own possibilities with every stray interaction? The line between the quantum world and our classical world became a battleground of ideas. Where does the spooky indeterminacy of the quantum wave end, and the solid, reliable reality of our everyday experience begin? Is there a line at all? The observer effect, as it came to be known, struck at the very heart of the scientific method. For centuries, science had operated on the assumption of an objective reality. A tree falling in a forest makes a sound whether anyone is there to hear it or not. The moon continues to orbit the Earth even when we are not looking at it. It was the foundational belief that there is a universe out there, separate from us, which we can study and understand. But the double-slit experiment with detectors presents a profound challenge to that assumption. It suggests that at the quantum level, the tree might only fall, or even exist as a definite tree in a definite location, when someone or something is there to register its fall. The unobserved universe might be a seething, undecided ocean of potential, and our measurements are the vessels that scoop out a tiny, temporary cup of certainty from that infinite sea. We had set out to solve a simple paradox about a particle's path. We sought to expose a trick, to understand a mechanism. Instead, we found ourselves staring into an abyss. We had uncovered a principle so strange, so contrary to our every intuition, that it felt like a message from an alien mind. The message was clear. The reality you perceive is not the totality of what is. The world is not a static photograph we are merely viewing. It is a dynamic participatory drama, and the act of observation is a form of creation itself. We are not just the audience, we are somehow, inexplicably, part of the cast. By trying to pin down the location of a single electron, we had stumbled upon one of the deepest and most unsettling truths in all of science. The very fabric of existence seems to respond to our questions, and the universe does not fully exist until we look at it. The implications ripple outward, touching everything we thought we knew about time, causality, and our own place in the cosmos. If an electron's past, whether it behaved as a wave or a particle, is determined by our choice to measure it in the present, what does that say about the flow of time? If reality is not fixed until it is measured, what does that mean for the vast, unobserved stretches of the universe? For the silent cores of stars or the empty voids between galaxies? Do they exist in a state of suspended, probabilistic animation, waiting for an act of observation to grant them a concrete history? We had opened Pandora's box, and inside we found not chaos, but a new and terrifyingly elegant order, an order in which the observer and the observed are locked in an inseparable embrace. The question was no longer simply, how does an electron go through two slits at once? The question had become something far more profound. What is reality? Is it a fixed stage upon which the laws of physics play out? Or is it an interactive script that we help to write with every measurement we take? The search for an answer would lead physics down even stranger paths, into a fractured world of competing interpretations, each more bizarre than the last, all desperately trying to make sense of the universe that looks back at us. And so, we are left here, on the edge of an intellectual abyss, staring into the unsettling chasm that has opened beneath the very foundations of reality. The experiment has given us its verdict, a judgment so profoundly strange, so contrary to every intuition we have ever held, that it feels less like a discovery and more like a cosmic sleight of hand. We have been shown the magician's trick, but not the secret. The act of looking, the simple, passive gathering of information, is revealed to be an act of creation, a force that wrenches a particle from a ghostly realm of infinite possibilities and commands it into a single, concrete existence. There is no quiet observation, there is only participation. The universe, it seems, does not perform for an empty theatre. It waits for an audience, and for our applause, it solidifies into the world we know. This realization is not a comfortable one. It dismantles the very idea of an objective, independent reality that ticks along, whether we are there to witness it or not. For centuries, science had been a process of pulling back a curtain to reveal the intricate, clockwork machinery of the cosmos. But the double-slit experiment suggests something far more unnerving, that when we pull back the curtain, the machinery hastily assembles itself, just for us, just in that moment. What is happening when the curtain is closed? What is the nature of a photon, an electron, an atom, when it is unobserved, flying through the dark? Quantum mechanics, in its most orthodox interpretation, gives an answer that is both mathematically precise and philosophically maddening. It says that before the measurement, the particle does not have a position. It is not a thing at a place. It is a cloud of potential, a wave of probability, a smear of existence described by a mathematical abstraction called the wave function. It is everywhere and nowhere at once, a pure idea waiting for the touch of reality. The architects of this new physics, men like Niels Bohr and Werner Heisenberg, embraced this radical vision. In what became known as the Copenhagen interpretation, they proposed that this probabilistic ambiguity was not a sign of our ignorance, but a fundamental feature of the universe itself. There is no deeper reality to find. The ghostliness is all there is, until an observation forces nature's hand. This was a monumental break from the past. It was a declaration that the world of the very small operates on a logic that is alien to our own, a logic of and/or rather than either/or. But for many, including some of its own pioneers, this was a pill too bitter to swallow. It felt like an abdication, a surrender to irreducible strangeness. It felt like saying the moon is not there when no one looks. The discomfort was so profound that it needed a new language to express its absurdity, a story to illustrate the sheer madness of it all. That story would come from the mind of Erwin Schrödinger, an Austrian physicist who had been instrumental in developing the very equations that now troubled him so deeply. In 1935, deeply dissatisfied with the Copenhagen interpretation, he devised a thought experiment, a Gedanken experiment, designed not to be taken literally, but to amplify the paradox to a scale so grotesque, so undeniably bizarre, that it would expose the flaws in this new quantum worldview. He wanted to drag the quantum ghost out of the subatomic shadows and into our familiar everyday world. He wanted to put it in a box, and with it, he put a cat. Imagine this diabolical contraption, a steel chamber, completely sealed from the outside world. Inside, a living, breathing cat. Alongside the cat is a tiny amount of a radioactive substance, so small that in the course of an hour, there is a perfect 50-50 chance that just one atom will decay. If the atom does decay, it triggers a Geiger counter. The Geiger counter in turn is wired to a hammer. The hammer is poised to shatter a small flask containing a lethal poison, hydrocyanic acid. The fate of the cat is now inextricably, terrifyingly linked to the fate of a single quantum particle. If the atom remains intact, the cat lives. If the atom decays, the cat dies. We seal the box, we start the timer, and we wait for 1 hour. Now, we must ask the question that drove Schrödinger to this grim fantasy. At the end of the hour, before we open the box, what is the state of the cat? Common sense screams at us with an obvious answer. The cat is either alive or it is dead. We just don't know which. The atom has either decayed or it has not. Our ignorance is the only thing in question. But this is where the Copenhagen interpretation extends its spectral hand from the quantum realm into the macroscopic world. According to its logic, the atom, unobserved, is not in a definite state. It has not decided whether to decay or not. It exists in a superposition of both states simultaneously, a ghostly blend of decayed and not decayed. And because the cat's fate is shackled to the atoms, the cat too must enter this state of quantum limbo. It must be, by this logic, both alive and dead at the same time. Not one or the other, but a perfect 50-50 superposition of life and death. A living ghost and a breathing corpse trapped in an impossible paradox. The very idea is a violation of everything we know. Life and death are mutually exclusive. They are absolutes. Yet, the mathematics of quantum mechanics, when followed relentlessly, leads us to this monstrous conclusion. The wave function describing the system inside the box would contain both a living cat and a dead cat. Only when we, the observer, intervene, only when we open the lid and let the light flood in, does the wave function collapse. Only then does reality snap into focus, forcing a choice. In that instant, and not a moment before, the universe decides. The atom resolves into a single state, and the cat is revealed as either tragically deceased or blissfully unaware of the probabilistic execution it just escaped. Schrödinger's point was that this was patent nonsense. A cat cannot be both alive and dead. Therefore, the interpretation that leads to such a conclusion must be in some fundamental way incomplete or incorrect. He had constructed a bridge from the fuzzy, uncertain world of the quantum to our solid, certain classical world, and he dared his colleagues to walk across it and accept the absurd landscape on the other side. This deep philosophical schism created a battle for the soul of physics. On one side stood Bohr and the Copenhagen school, who argued that our classical language and intuition simply fail when describing the quantum world. The paradox only seems like a paradox because we are trying to apply large-scale rules to a domain where they do not belong. They insisted that the superposition is real, and the measurement is what creates the definite outcome. On the other side stood a powerful group of dissenters, chief among them Albert Einstein. His famous declaration, "God does not play dice," was not just a witty remark, it was a profound statement of philosophical belief. Einstein could not accept that the universe was governed by pure chance at its most fundamental level. He believed that the probability we see in quantum mechanics is a sign of our own incomplete knowledge, not a feature of reality itself. He argued for the existence of hidden variables. Perhaps the particles are not just waves of probability. Perhaps they are always particles, with definite properties like position and momentum, properties that are simply hidden from us. Like a magician's coin that seems to appear from nowhere, maybe the electron always knows which slit it will go through. Maybe it is guided by some underlying deterministic physics that we have not yet discovered. In this view, the wave function is not a complete description of the particle. It is a statistical tool that reflects our ignorance of these hidden variables. If we only knew all the variables, we could predict the outcome with absolute certainty. There would be no randomness, no superposition, no alive and dead cat. There would only be a complex, beautiful, and ultimately predictable clockwork, just as Newton had envisioned. For decades, this debate raged. Was the strangeness real, or was it a veil hiding a deeper, more sensible order? It seemed an impossible question to answer, a matter of philosophical taste rather than scientific inquiry. How could you ever prove or disprove the existence of variables that are, by their very definition, hidden from you? The question hung in the air for nearly 30 years, a stalemate between two of the greatest minds in history. Then, in the 1960s, a physicist named John Bell devised a brilliant theoretical proof, a theorem that could finally put the debate to an experimental test. Bell's theorem was a masterpiece of logic that showed if Einstein's hidden variables were real, then certain correlations between entangled particles would have to obey a strict mathematical limit. But if the strange rules of quantum mechanics were correct, that limit could be violated. It was a gauntlet thrown down to the experimentalists. The stage was set for a definitive test, one that would force the universe to show its hand. And when the experiments were finally performed, with ever-increasing precision over the following decades, the results were unequivocal. Bell's limit was broken, time and time again, in laboratory after laboratory around the world. Einstein, it turned out, was wrong. God, it seems, does play dice. The strangeness is real. There are no hidden variables pulling the strings behind the scenes. The universe is, at its core, genuinely, irreducibly weird. But if this crushing verdict seemed to settle the matter, it was only the prelude to an even deeper and more confounding mystery. The acceptance of quantum superposition as a real phenomenon, not just a mathematical convenience, opened the door to a question so bizarre it sounds like it belongs in science fiction. It came from the mind of another titan of physics, John Archibald Wheeler, a man who saw the quantum world as a canvas for the most imaginative and challenging ideas. Wheeler took the core lesson of the double-slit experiment. That observation defines reality, and he decided to push it to its absolute mind-bending limit. He asked, what if the choice to observe is made after the particle has already completed its journey? What if we could somehow decide whether to measure which path a photon took after it should have already hit the detector screen? This is the delayed choice experiment. Let's reconstruct this almost diabolical setup. Once again, we have a source firing single particles, one at a time, towards a screen with two slits. But this time, the final detector screen is not fixed. It can be removed at a moment's notice. With the screen in place, we are performing the classic double-slit experiment. A particle passes through the slits, its wave of probability interferes with itself, and over time, it contributes to building the telltale interference pattern. This is the wave-like behavior we have come to expect. Now, for the twist. We set up two powerful telescopes, each one aimed precisely at one of the slits. If we remove the final screen at the last possible nanosecond before the particle arrives, we can instead use these telescopes to see which slit the photon actually emerged from. This act of measurement, as we know, will force the photon into a definite path. It will behave like a particle. If we do this for every photon, we will see two distinct clumps on our detectors behind the telescopes, one for each slit, no interference pattern. Here is Wheeler's profoundly unsettling question. The decision to either leave the screen in place to observe wave behavior, or to remove it and use the telescopes to observe particle behavior, is made long after the photon has passed through the slits. Let that sink in. The photon is already on its way. In a classical world, it has already chosen its path. It either went through one slit, like a tiny bullet, or it went through both, like a wave. Its history is, supposedly, written. But now, we, the experimenters, make a last-minute choice. If we leave the screen in, the photon that arrives must have behaved like a wave, going through both slits to create the interference. If we snatch the screen away and use the telescopes, the photon we detect must have behaved like a particle, going through only one slit to be seen. How can the photon know what we are going to do? How can our future choice possibly influence its past behavior? It seems to imply a kind of retroactive causality, a message sent backwards in time. Does our decision in the present force the photon in the past to retroactively change its mind? Did it travel as a wave, only to collapse its own history into a single path the moment we decided to look? Or did it travel as a particle, only to retroactively spread itself out into a wave the moment we chose not to? The proposition is so outlandish it borders on the mystical. It tears at the very fabric of causality, the sacred principle that a cause must always precede its effect. Yet, when Wheeler's thought experiment was finally brought to life in the lab, the results were as clear as they were shocking. The universe obeyed the quantum prediction, without fail. When the experimenters chose to leave the screen in, they got an interference pattern. This meant that the photons had, for all intents and purposes, behaved as waves and travelled through both slits. When they chose to pull the screen away at the last second and use the telescopes, they detected photons coming from one slit or the other, but never both. No interference pattern was formed. The photons had behaved like particles. The particle's past, its history of being a wave or a particle, seemed to be determined by the choice of measurement made in its future. It is as if we are co-authors of the past. It's not that we are changing the past. The implication is far more profound. Wheeler's experiment suggests that the past of an unobserved particle is an open book, a story that has not yet been written. It exists only as a spectrum of possibilities. It is our measurement, our question, that reaches back and solidifies one of those possibilities into a concrete history. The particle does not have a past until we ask it for one. We are forced to confront a reality that is not a static, pre-existing thing. It is a dynamic, participatory process, a conversation between the observer and the observed that echoes not just in the present, but ripples backwards through time itself. The solid ground of cause and effect, the linear progression of history from a fixed past to an open future, begins to dissolve into a shimmering quantum haze. We are no longer just passive onlookers cataloguing the universe's artifacts. We have become implicated in the very story of its creation, moment by moment. The cat in the box was a paradox of the present. The delayed choice experiment is a paradox of time itself. We have peered deeper into the quantum rabbit hole only to find that it does not just go down. It seems to loop back on itself, twisting our notions of before and after into an unrecognizable shape. And this temporal strangeness raises an even more staggering question. If our choices can define reality in the lab, what role do we play on a grander cosmic scale? What other phantom realities are waiting in the wings, waiting for a question to be asked before they can claim to have ever existed at all? Faced with this quantum ghost, this particle that behaved like an apparition, the greatest minds of the 20th century were thrown into a profound intellectual crisis. The elegant, predictable clockwork of Newton's universe had been shattered. In its place was a funhouse mirror, reflecting a reality that seemed to warp and shift depending on how you looked at it. This wasn't just a quirky experimental result. It was a dagger pointed at the very heart of objective reality, the core assumption of all science. The evidence was undeniable, the mathematics impeccable, yet the meaning was an abyss. Into this void, scientists and philosophers alike were forced to leap, armed not with instruments, but with ideas. They had to construct a bridge of logic over the chasm of the unknown, to build a story that could somehow contain this madness. They had to interpret what the universe was screaming at them, and in doing so they would unleash a battle for the soul of physics that rages to this very day. From the intellectual maelstrom of Copenhagen, a city that became the Vatican of the new quantum faith, emerged the first and most dominant dogma. Championed by the formidable Niels Bohr and his brilliant intense protégé Werner Heisenberg, it became known as the Copenhagen interpretation. It is an idea born of radical pragmatism, a philosophy that stares into the quantum abyss and, rather than trying to map its depths, simply declares a boundary. The interpretation doesn't try to explain the weirdness away. It enshrines it as a fundamental law of nature. At its core is a stark and unyielding division of the cosmos into two separate domains, the quantum and the classical. Down there, in the realm of electrons and photons, things are governed by the strange, ghostly mathematics of probability waves described by the Schrödinger equation. An electron isn't here or there. It exists as a smear of potential, a cloud of possibilities, all coexisting simultaneously. But up here, in our world, the world of scientists and detectors and laboratory benches, things are definite. A dial points to a specific number. A screen shows a distinct point of light. The Copenhagen interpretation argues that the act of measurement is the bridge, the violent collision between these two realities. When your detector intercepts that electron, it forces the quantum world to abandon its ambiguity. This isn't a gentle uncovering of a pre-existing reality, like lifting a sheet to see what lies beneath. It is, according to Bohr, an irreversible act of creation. The wave function, that beautiful mathematical description of all possibilities, is said to collapse. From an infinite spectrum of potential positions, one, and only one, is randomly actualized into our classical world. Before the measurement, the electron was a wave passing through both slits at once. After the measurement, it is a particle that definitively went through only one. Where was it before we looked? Bohr's answer was as profound as it was infuriating. The question is meaningless. It is fundamentally unscientific to ask about properties of a system that are not being measured. To speak of the electron's path, when you aren't tracking it, is like asking about the marital status of a unicorn. There is no hidden reality, no secret mechanism orchestrating the outcome. There is only the wave of probability, and then, after the intrusive act of a classical observer, a concrete result. This observer isn't just a passive witness, they are an active participant, a co-creator of reality itself. The line between the knower and the known dissolves into a fuzzy, indefinable boundary. This idea was philosophical dynamite. It suggested a form of cosmic censorship, a fundamental limit on what we can ever know about the universe's true nature. It implied that reality at its most fundamental level is not deterministic, but irreducibly random. The universe, it seemed, plays dice. This was anathema to physicists like Albert Einstein, who famously railed against it, believing that a deeper, more orderly reality must lie beneath the quantum chaos. He felt that the theory, while mathematically successful, was incomplete. It was like describing a storm by only cataloguing where the raindrops land, without ever acknowledging the existence of clouds or wind. He searched relentlessly for cracks in Copenhagen's logic, devising thought experiments to expose its inherent strangeness. He derided the idea of instantaneous wave function collapse across vast distances as spooky action at a distance, a clear violation of his own firmly established speed limit for the universe, the speed of light. But Bohr and Heisenberg held their ground. They argued that the wave function wasn't a physical object spreading through space, but a mathematical tool, a statement of our knowledge about a system. When you make a measurement and gain new information, your knowledge changes instantly, and so the wave function collapses everywhere at once. For decades, this interpretation, despite its philosophical baggage and the deep discomfort it induced, became the default textbook explanation. It worked. It provided a practical, if philosophically jarring way for physicists to calculate and predict, to build lasers and transistors and atomic clocks. They were told, in essence, to shut up and calculate. But for some, the instruction was impossible to follow. The ghost in the machine was too large, the implications too profound to simply be ignored. The idea that our very act of looking could conjure a reality from a mist of probability felt less like science and more like magic. The search for a more palatable, a more complete description of reality was far from over. In 1957, a brilliant but obscure graduate student at Princeton named Hugh Everett III proposed an alternative so audacious, so wildly imaginative, that it was initially dismissed as science fiction. He looked at the central mystery of the Copenhagen interpretation, the collapse of the wave function, and proposed the simplest, most radical solution imaginable. What if, he asked, it never collapses at all? What if the Schrödinger equation, which so perfectly describes the evolution of the quantum wave, is the only rule? What if it applies not just to electrons and photons, but to everything, to detectors, to lab equipment, to scientists, to you? If that were true, then the moment a measurement is made, the moment the electron's wave of possibility interacts with the observer, something extraordinary must happen. The observer, being a quantum system themselves, doesn't force a collapse. Instead, the entire system, electron, detector, and observer, enters a state of massive superposition. In one branch of this new, larger reality, the electron is detected at the top of the screen, and the scientist sees it at the top of the screen. But in another perfectly real branch, the electron is detected at the bottom, and a version of that same scientist sees it at the bottom. Every single quantum measurement, every potential outcome doesn't just remain a possibility, it becomes an actuality. The universe at that moment splits. This is the many worlds interpretation. It posits that our reality is just one branch on an endlessly proliferating cosmic tree. Every quantum event, from the decay of a radioactive atom to the path of a photon from a distant star, causes the universe to cleave into a dizzying number of parallel realities. In one universe, the particle went through the left slit. In another, identical in every way up until that instant, it went through the right. And in both universes, a version of you exists, utterly convinced that your reality is the only one, completely unaware of your countless twins living out the consequences of every other quantum possibility. This theory resolves the measurement problem with breathtaking elegance. There is no special role for the observer. There is no mysterious collapse. There is no fundamental randomness. The mathematics is pure, continuous, and deterministic from start to finish. The wave function simply evolves, and we, as inhabitants of just one of its myriad branches, only experience a fraction of the total picture. The apparent randomness we perceive is merely an illusion, the result of our ignorance about which branch we happen to occupy. The ontological cost, however, is staggering. To save the integrity of the quantum math, you must accept the existence of an infinite or near-infinite number of parallel universes. There are universes where you accepted that job offer, and universes where you declined. Universes where you turned left instead of right. Universes where the dinosaurs were never wiped out. Universes where the fundamental constants of physics are slightly different, leading to realities so alien they would be incomprehensible. It is a vision of the cosmos of almost unimaginable grandeur and extravagance. Our entire perceived reality, our whole cosmic history, becomes just a single sliver, one volume in an infinite library of universes. For many physicists, this is a price too high to pay. They argue it violates the principle of Occam's razor, that the simplest explanation is usually the best. Why postulate an infinity of unobservable worlds just to solve a problem in our own? The theory is also, by its very nature, untestable. We are permanently locked within our own branch of reality. We can never peek into the others to confirm their existence. They leave no trace, no shadow on our own world. Yet for its proponents, the many worlds interpretation is the most logical, the most mathematically consistent, and the most courageous conclusion to draw from the quantum evidence. It takes the equations at face value and follows them to their ultimate spectacular conclusion. It suggests that the wave pattern seen in the double-slit experiment is no mere abstraction. It is the literal shadow of the particle's other selves in other universes, interfering with the one we happen to be observing. The weirdness isn't just in the math, it's in the very fabric of a multiverse so much larger and stranger than we could ever have conceived. It is an idea that replaces the quantum mystery with a sense of profound cosmic vertigo. But what if there was another way? A path that avoids both the philosophical paradoxes of Copenhagen and the ontological excess of many worlds? What if the problem wasn't that our understanding of reality was too simplistic, but that it was incomplete? This was the conviction of one of quantum mechanics' own founding fathers, Louis de Broglie, and later revived and championed by the brilliant physicist David Bohm. Their idea, known as the pilot wave theory or Bohmian mechanics, is a return to a more classical intuitive picture of the world. It proposes a reality of hidden variables, a deeper layer of information to which we are not typically privy. In this view, the electron is not a wave or a particle. It is both, simultaneously and at all times. There is a real, definite particle, an object with a precise position, whether we are looking at it or not. It is not a nebulous cloud of probability. It is a point, a tiny billiard ball travelling on a determined trajectory. So where does the wave-like behaviour come from? De Broglie and Bohm argued that the particle is accompanied by a pilot wave. This is a real physical wave, also described by the Schrödinger equation, that permeates all of space. The particle is like a surfer, and the pilot wave is the ocean. The wave itself is invisible, but it guides the motion of the particle, pushing it and pulling it along a specific path. The particle doesn't create the wave, and the wave isn't just a mathematical tool. They are two sides of the same cosmic coin, an inseparable pair. When this particle and wave combination approaches the double slits, the setup becomes crystal clear. The tiny, solid particle itself only ever goes through one slit, just as our intuition demands. But its associated pilot wave, being a wave, goes through both. As the wave emerges on the other side, the two parts of it interfere with each other, creating a complex pattern of crests and troughs, peaks of high intensity and valleys of calm. This interference pattern in the underlying pilot wave then acts like a series of invisible channels, guiding the particle to land on the detector screen in the high-intensity regions and avoid the low-intensity ones. Over time, as many particles make the journey, they trace out the familiar interference pattern, not because each particle is a wave, but because each particle is being expertly guided by one. The mystery of wave-particle duality simply vanishes. The theory also elegantly explains the observer effect. When you place a detector at one of the slits to see which way the particle goes, the very act of measurement disturbs the delicate pilot wave. It's like putting a large rock in a calm pond. The interaction is so significant that it completely alters the shape of the wave, washing out the interference pattern. The subsequent particles are then guided by this new, non-interfering wave, and they create the simple, clumped pattern of solid objects. There is no wave function collapse, no splitting of universes. There is just a cause and an effect, a simple physical interaction between your detector and the pilot wave. On the surface, this interpretation seems like the perfect solution. It restores objectivity. The world exists with definite properties independent of our observation. It restores determinism. If you knew the exact initial position of the particle and the shape of its pilot wave, you could predict its final destination with perfect accuracy. The apparent randomness of quantum mechanics is simply a result of our ignorance of these hidden variables. The universe is not playing dice. It is a perfectly wound clock, its gears just hidden from our sight. But this beautiful classical restoration comes at its own strange price. The pilot wave is a deeply weird entity. For this theory to work, the wave must be non-local. This means that the state of the wave at any given point in space depends on the state of the entire system, everywhere else in the universe, at that exact same instant. A change in the wave here could instantaneously affect the wave on the other side of the galaxy. This is precisely the spooky action at a distance that so troubled Einstein, a blatant violation of the cosmic speed limit. For many physicists, this non-locality, is an even greater conceptual hurdle than the paradoxes of Copenhagen or the extravagance of many worlds. It paints a picture of a universe that is profoundly interconnected, a single, indivisible whole where every part is in instantaneous communication with every other part. It is a holistic, almost mystical view of reality, one that shatters our common sense notions of space and separation. And so, the community found itself fractured, caught between three profoundly different visions of reality. One that says reality is created by observation, one that says all possible realities exist, and one that says reality is deterministic but connected in ways that defy our deepest intuitions about space and time. Each interpretation accounts for the double-slit experiment. Each one is consistent with the known mathematics, yet they describe universes that are fundamentally, irreconcilably different from one another. They stand as towering, competing monuments of human ingenuity, each a desperate attempt to make sense of an experiment that refused to be sensible. The battle lines were drawn, not on a physical field, but in the abstract realm of scientific philosophy, a conflict over the very meaning of the word real. This wasn't just an academic debate. The choice of interpretation subtly colours the direction of future research, hinting at what kinds of questions are even permissible to ask. Does it make sense to search for a deeper theory? Or have we already hit the bedrock of reality? Is the universe a single, unfolding story, or an infinitely branching epic? The lack of consensus left a chilling possibility hanging in the air. What if the quantum world is not just strange, but fundamentally beyond the grasp of human intuition? What if our minds, evolved to track predators on the savannah and throw spears, are simply not equipped to comprehend the ultimate nature of existence? The pioneers had opened Pandora's box, and now we, their inheritors, were left staring inside. And so we stand at the edge of the abyss, having erased the past. We have pulled a phantom back from the void, restoring an interference pattern by deliberately forgetting which path a particle took. It is a conclusion so utterly defiant, so completely alien to the granite-solid logic of our everyday world, that the mind recoils. We want to find the flaw, the hidden variable, the piece of celestial sleight of hand that would restore our comfortable classical reality. We search for the magician's secret, but we find only the raw, unfiltered magic of the universe itself. For 2 centuries, the brightest minds in human history have thrown themselves against this problem, designing ever more elaborate, more ingenious, and more mind-bending versions of that simple screen with 2 slits. They have shot photons, electrons, and even buckyballs, molecules of 60 carbon atoms, veritable cannonballs on the quantum scale. They have delayed the choice of measurement until the particle has long since passed the barrier. They have devised ways to peek at the information and then erase it from existence. Yet after every attempt to corner it, to force it to confess its secrets, the central paradox remains, not as a stubborn anomaly, but as the unshakable foundation of our physical world. It is the ghost in the machine of reality, a ghost that refuses to be exorcised. This journey we've taken from a simple candlelit room in the early 1800s to the sterile, laser-etched precision of modern laboratories was never just about light. It was about us. It was a journey into the very meaning of the word is. Before this experiment, existence was a simple affair. A thing was either here or it was there. A baseball once thrown follows a single, definite path from the pitcher's mound to the catcher's mitt. We could calculate its trajectory, its spin, its velocity. We never for a moment entertained the notion that it might have taken every possible path simultaneously. It was a concrete object, an actor on a well-defined stage, following a script written by the immutable laws of classical physics. The double-slit experiment took that script, that entire conception of a solid and reliable reality, and set it ablaze. It revealed that on the most fundamental level, the universe does not operate on a logic of certainty, but on a mesmerizing ethereal logic of possibility. Before the act of measurement, before our interaction, the electron is not a tiny ball hurtling through space. It is something far more mysterious. It's a whispered promise of a particle. It's a wave of pure potentiality, a mathematical abstraction that permeates the space of all possible outcomes. To ask where it is before we look is a meaningless question. It is like asking the colour of a dream or the specific address of a melody. The question itself assumes a classical reality that simply does not apply. The particle's existence is conditional, a form of becoming rather than a state of being. It is spread out, not as a physical substance, but as a field of information, a ghost wave exploring all avenues at once. This is not a metaphor. According to the standard interpretation of quantum mechanics, this is the literal mathematical truth. The universe, it seems, does not commit. It keeps its options open. Only when we intervene, when we force the issue by setting up a detector to ask, "Which way did you go?" does this cloud of potential collapse. It is an instantaneous, violent crystallization of reality. Out of an infinity of possibilities, one single solitary actuality is born. In that moment of interaction, the wave vanishes, and a particle appears, a point-like event at a specific location. We find our answer. But in the very act of asking the question, we have fundamentally altered the nature of the universe we are observing. We have traded the ethereal mystery of the wave for the mundane certainty of the particle. We have sacrificed the beautiful, ghostly interference pattern, the evidence of its simultaneous journey, for a single piece of information. We wanted to know its past, and in doing so, we forced it to have only one. This is the profound bargain of quantum mechanics. You can know the path, or you can witness the interference. You can have the particle, or you can have the wave, but you can never, ever have both at once. This forces us into a radical rethinking of what it means to be an observer. In our classical world, we are spectators. We watch the planets orbit the sun, we measure the speed of a cheetah, we record the eruption of a volcano. We assume, implicitly, that our act of watching has no effect on the event itself. We are separate, detached, peering through a one-way mirror at the grand cosmic drama unfolding before us. We are the audience. The universe is the stage. But the double-slit experiment shatters this illusion of separation. It tells us that the one-way mirror is, in fact, a doorway. By observing, we are not passive witnesses, we are active participants. The universe, it seems, performs differently when it is being watched. The line between the observer and the observed, that clear, sharp distinction that has been the bedrock of all science, dissolves into a blurry, inseparable union. We are not just cataloguing a pre-existing reality. Our measurements, our questions, our very thirst for knowledge are woven into the fabric of the reality that is produced. This is not a statement about consciousness. It is not to say that our minds alone conjure the moon into existence. A mindless Geiger counter, a photographic plate, any device capable of irreversibly recording which path information will have the same effect. The universe doesn't care about our awareness, it cares about information. The moment information about a particle's path is created and stored in the wider environment, the moment a permanent record is made, the quantum superposition is broken, the wave-like magic vanishes. This interaction is the key. Reality, at its deepest level, appears to be a profoundly interactive process. Existence is not a static state, but a dynamic relationship. It is a conversation between the quantum system and the measuring apparatus, and we, the scientists, are the ones who build the apparatus and ask the questions. This elevates our role from mere discoverers to something far more profound. We are not just mapping a territory that was already there. We are, in a very real sense, co-creators of the map. The questions we choose to ask the universe directly influence the answers it is able to give. If we ask a particle-like question, "Where are you?" the universe provides a particle-like answer. If we ask a wave-like question, by allowing for interference without peaking, the universe provides a wave-like answer. It holds up a mirror to our own interrogation. This has led some of the most brilliant physicists to the brink of mysticism, forcing them to confront the possibility that what we call reality is not an objective, independent entity that we slowly uncover. Instead, it might be a participatory process, a collaborative dance between the potentiality of the quantum world and the actuality created by measurement. The universe, in this view, is not a finished book that we are learning to read. It is a story that is being written, and our observations are the very ink with which the next sentence is inscribed. This experiment, then, is far more than a historical curiosity or a chapter in a physics textbook. It is a living, breathing enigma. It is the taproot from which the entire strange and wonderful forest of quantum mechanics has grown. The principles it revealed, superposition, wave-particle duality, the measurement problem, are not abstract footnotes. They are the engine of our 21st century technological revolution. The bizarre behaviour of that single electron passing through two slits is the foundational principle behind the laser in your Blu-ray player, the transistors that power your smartphone, and the promise of quantum computers. These devices, which will one day solve problems utterly beyond the reach of any classical machine, are being built not by ignoring the strangeness of the quantum world, but by embracing it, by harnessing the ghost in the machine. Quantum computing, in essence, is the double-slit experiment on an industrial scale. It allows a quantum bit, a qubit, to explore a vast landscape of possible solutions simultaneously, just as our electron explored all possible paths, collapsing into the single correct answer only at the very end. We are learning to speak the universe's native probabilistic language, and it is giving us the keys to a new kingdom of technological possibility. The experiment also forces us to confront the nature of information itself. In quantum cryptography, the very act of an eavesdropper trying to observe a secure communication to measure which path a photon took inevitably disturbs the system, collapsing the wave function and alerting the intended recipients. The central mystery of the double slit has become the ultimate guarantee of privacy. Yet, for all the technology it has spawned, the fundamental questions remain unanswered, and perhaps they are unanswerable. Why does the universe behave this way? Why does the act of observation have this seemingly magical power to transform potentiality into actuality? What truly constitutes a measurement? Does it require a large-scale classical object? Does it require the irreversible loss of information to the environment, a concept known as decoherence? Or does it, as some daring thinkers have proposed, require a conscious mind at the end of the chain? We do not know. The greatest minds of our time disagree, often vehemently. There are interpretations that propose a multitude of parallel universes, one for each possible outcome, splitting off from our own with every quantum event. In this many worlds view, the electron really does go through both slits, but in different, equally real universes. There are other theories suggesting hidden variables, a deeper layer of reality we haven't yet accessed, that would restore a deterministic classical order. But to date, every experimental test has ruled against these local hidden variables, confirming the deep and irreducible strangeness of the quantum world. The universe seems to revel in its ambiguity. It seems to enjoy being a superposition of wave and particle, of mystery and fact. And so, we are left here, at the end of our journey, not with a neat and tidy solution, but with a more profound and beautiful question. We have been humbled. The confident clockwork universe of Newton has dissolved into a shimmering sea of probabilities. The notion of a simple, objective reality that exists independent of us has been irrevocably shaken. We are left staring into the heart of a great mystery, a mystery that touches upon the very nature of existence, of information, of our own place in the cosmos. The double-slit experiment serves as a permanent and powerful reminder of the limits of human intuition. It teaches us that the universe is under no obligation to make sense to our primate brains, which evolved to dodge predators on the savannah, not to comprehend the fundamental nature of being. It challenges us to let go of our most deeply ingrained assumptions, to embrace uncertainty, and to accept that the world may be far more subtle, more interconnected, and more marvellous than we ever imagined. It is a lesson in intellectual humility, a cosmic koan that silences our arrogant demand for simple answers. It doesn't offer us a final truth, but instead, it offers us something far more valuable. It gives us a reason to keep asking, to keep exploring, to keep pushing the boundaries of what we know. It is a gateway to wonder. It forces you to look up at the night sky not as a collection of fixed, distant objects, but as a vast, unfolding quantum experiment, a place where possibility reigns supreme, and where the simple act of looking might just be part of the show. The story of reality is not yet finished, And we, it turns out, are not just the readers. We are the authors.